Serbian Academy of Science and Arts in Serbia. From 2011, you have been a principal investigator on a grant funded by the National.
So, well, thanks again for being a part of this. And so we're going to talk about nanobiotech. Okay, the first part. Of course, yeah, just come in. So you guys can introduce yourself later, I guess, during the break. So nanobiotech, a very fancy word. Many people I meet, when I talk about science in the United States, where I work, a lot of people think that it's kind of a too hype of a word, right? Like everybody wants to do nanobio these days, and I think that's actually going to be even more and more prominent. So, but I think it's it's not gonna hurt anyone here to learn more about this subject. And so let's start slowly. We're gonna go, slide by slide. At one point, I'm gonna speed up this information. So I'm gonna see that in your faces. You're gonna be really tired because you're gonna be overwhelmed with so much material. But I think it's better than just, covering, very little here and there. So, okay, so let's go one by one. So here I give you a couple of titles, just in order to illustrate to you that, nanobiotechnology or bionanotechnology, whichever, and we're going to talk about that. Is there any difference between the two? Is, there's many titles, many books these days, and as I say, it's just the beginning. This field is going to take over, and it's going to be, the future of science, really. So what is what is nanobiotech, as I said? So that's the question. I work with students, and I realize, it's quite a challenge for them to learn how to describe their science. So typically students who are very good in hands-on work are not so great in terms of, being eloquent, right? And the other way around. I have students who are, relatively lazy, but they're very smart and they can very well tell you what they do. And so, I have yet to meet a person who's, diligent and very hands-on, but at the same time very eloquent. So why am I telling you this? Because, when I work, so let's say on papers with students, so what I tell them, okay, they're stuck. They don't know how to write an introduction. So I said, okay, start by just defining the words that you use in your title. So define every single word. What is that? Why that? Why? And then that's going to be just good of a start. So nanobiotechnology. So how do we define that? Does anyone have any idea? So it's a composite word, right? It has nano and bio. Okay, so nanotechnology, it's if you probably know, and you can even find it in Wikipedia. That's the science of that's actually technology of the the application of the science of nanostructures. What are nanostructures or nanomaterials? These are the materials that have critical boundaries on the scale that is lower than 100 nanometers. So critical boundaries usually mean the size of the constituent units, such as particles or crystals inside of a material. There could be other, critical boundaries that actually pertain to specific physical effects, so not necessarily to spatial dimensions. So that is nanotechnology. Now, what is nanobiotechnology? The question is, as I say here, is that the application of nanomaterials in the biomedical domain? That is actually what most people tend to think these days, that nanobiotechnology is the use of nanostructured materials and their application for biomedical purposes. So, but again, as you shall see very soon, we can ask these questions. We can ask ourselves, what if nanobiotechnology is actually the science of the application of nanomaterials in biotechnology? So what is biotechnology? Traditionally, it's been, a science of, say, when you make insulin in bacteria, that's an example of biotechnology, or when you harness biological, materials, biological organisms to create something. So, biofuels, for example, another biotechnological method. So, so what if bionanotech is something like that, right? A completely different thing. Another thing it could be is the science of the application of biology in creating nanomaterials. So we're gonna, I'm just giving you these questions, and we're gonna slowly start to reveal them. So another thing, believe it or not, but I'm the director of this lab, and most of the time I don't know what the name of my lab is. Why? Because I constantly confuse, and I never know whether it's nanobiotechnology or bionanotechnology. So have we defined the difference? No, nobody knows the difference. Why? Because this is such a new and very vaguely defined field of science. It's not even at a crossroad. It's actually kind of just, it's in a very embryonic stage. So, so all these things are, you know, I mean, we can sit here and discuss this for hours. You know, what would be nanobiotech and what would be bionanotech? So, you know, what sometimes when I tell my students, you know, I propose this as an example, like what if nanobiotech would be the use of nanotechnologies for biotechnological purposes? And what if biotechnology, what if bionanotech would be actually the use of biological materials to create new nanotechnologies? So, so this is, you know, this is something that everybody knows here, and I don't have to talk about Bhagavad Gita, right, here, because I'm in India, right? Yes, this is my second day, but I'm tired of all the trip, but I know where I am. So the way I see that, it's kind of like a clash, you know. So when you talk about nanobiotech, you have a clash of two armies, you know, two peoples with completely different type of thinking. And that's what Bhagavad Gita is, right? You have Arjuna, who's out there on the battlefield, and Krishna comes and he shows him, you know, there's this army on one side, the other army on the other side. And so you're standing in the middle, and, you know, so clearly there's a metaphor of dialectical, you know, confrontation between two opposites, right? And so when you look at the science of biology and the science of nano, you'll realize that these are two vastly different sciences. So science of biology is a soft science. That's the epitome of soft science, right? It's very qualitative. It relies on a very, very different methodology, I would say, right? On the other hand, you have nano, which is a sub-discipline of material science, right? So when you have material scientists and biological scientists in the same room, it's very difficult to make them actually talk about science together. I have a friend who works he's an editor for Nature, and their offices in New York City are actually designed in such a way that they are physically divided. So you have biologists and, you know, life scientists on one side, and you have material scientists and physicists and chemists on completely different part of, you know, kind of like their offices, so totally do not interact. And so, so if you want to be a successful scientist in nanobiotech field, you clearly have to do what Arjuna does here, kind of being between the two armies. You have to learn how to speak the two languages at the same time, and these two languages are very, very different. You know, the language of biology is the language of, you know, molecular recognition. Is the language of, as I said, qualitative language. Is the language of extensive use of statistics. In material scientists, very often you plot graphs and there's no standard deviation, right? Because if you analyze the material right now and like 10 minutes later and 10 days later, they're going to behave more or less the same. And so for a biologist, that sounds horrible, like a sin, you know, like you're presenting data without a standard deviation. Of course, when you work with cells or biological entities, you know, they're subject to tremendous changes from one moment to the next. So naturally, we have to rely on, you know, more biostatistics and everything. So so how to become fluent in two languages at the same time? That's kind of a challenge for me in my work, and for anyone who does anything that could be called bionanotech. So I have yet to meet a person who's fluent in these two languages. So most of us, you know, graduated, got our education in one of them, and then over time, we kind of learn a little bit about the other. The same is with me. The same is with everyone I have met. I'm a material scientist. I'm a physical chemist. And so over time, I actually realized the potential of this cross-fertilization of material science on one side and biology on the other. And so I got interested in that. To tell you the truth, I was actually very jealous about my biologist friends. I was working in a scientific institute, and I thought they are much more curious personalities. So I thought, you know, they work with cells, with biology, so it's kind of a more animate matter. So as a result, I became very curious. I got a chance to work on biology. I got specialization in there. But in any case, I'm still a material scientist, and I will never speak the language of biology as well as a biologist does, including molecular biologist or biochemist. Another thing is that, at the end of the first chapter of Bhagavad Gita, there's probably, for me, the most striking moment when Arjuna says, "I can't fight. I don't want to fight." But Krishna tells him, right, you have to pick a side. So you would expect that, maybe he would tell him, stand in the middle or be a peacemaker or something like that. But no, he tells him, pick a side and go on and fight. So, whatever the repercussions are for the transcendental philosophy there. But so that brings me to the point that all of us are always going to be inclined to one side, and that's just totally fine. And you shall see that what is the way to solve this problem? Interdisciplinary efforts, right? Collaboration, talking to people. Like if I'm a PhD in material science, I'm obliged to talk to medical scientists, to biologists, to biochemists, etc., to solve the problems in my science. I cannot anymore allow to be isolated in a hole in the ground, basically, which used to be an old model for science, right? You are sitting in your own office, that's your own universe, and you work on science. But that model doesn't work anymore. So science has become increasingly collaborative, increasingly interdisciplinary, and we have to, we just don't have any other choice but that. And it's a very difficult challenge for us, because as a scientist, and most of you are introvert personalities. I am very introvert, and it's quite a challenge actually to stand here and talk to all of you, because I would rather, be in your place and just sit back and, be confined in my own little universe. But, comes the time that when we have to, jump out and share our knowledge and communicate that to others. So, so let me give you a little bit of background, because, the next 4 or 5 days are going to be a lot about piling up the facts. Because you should see, we're not sure what this field nanobiotech is. So we're going to talk a lot about materials and methods for making nanomaterials. We're going to talk about nanotechnologies, and then go to, cell biology and characterization of materials in terms of their biological response, etc. So it's going to be, a very chaotic walk. But I want to give you just a little bit of awareness as to what biomaterials are. So let's go. What biomaterials, what nanostructure biomaterials are. So for every scientist working in the biomaterials field, this is the ultimate ideal: a bionic man, a man that is integrated with technologies. So how many of you, if any, I think most of you are young, to have any technological device implanted inside of you? No one, and that's good. I think that's great. So mostly, as people get older, there's a need to fix certain issues that go wrong in the body, and oftentimes, the doctors, whatever, prescribe, implantation of a device or a material. Now, that is another ultimate ideal of the biomaterials field. That's a whole man, in a sense. Sooner or later, something goes wrong with our bodies, and we need to fix that. How do we fix that? We could fix that with biomaterials. So, and if we use the regenerative approach, which is one of the 2 central approaches in biomaterial science, it's here on the right. This is not, I don't have, maybe I have batteries. I really apologize. Maybe by tomorrow. So anyway, we'll continue without my pointer. But in any case, so with the regeneration, the idea is to fix something and then to let that biomaterial disappear from the body. So in a way, the material would degrade itself and at the same time heal whatever was wrong with the body. So that is one of the central approaches in the biomaterial science, and actually that approach has taken over, biomaterials almost completely. Another approach is augmentation, which means to augment the body, to make it actually capable of things that otherwise it would not be capable of. And that's more of a science fiction, direction in biomaterial science. So, so try to be aware. One of them is trying to regenerate the human body and bring it to the previous state. It's kind of assuming that the human body, as it is the most perfect of the state that we could, strive to achieve. The other approach is more kind of imaginary, more sci-fi. You could call it more Frankensteinian in essence, right? Trying to build something that's actually going beyond the human body. It goes back to the metaphor Icarus, and Daedalus. Daedalus gave Icarus the wings to actually go beyond, yes. And it melts away because he was not following the middle path, right? So he approached the sun too close and got melted. But if he had followed the middle path, maybe he would have flown further. So, and this is the current state of the art. Now, the bionic man is beautiful as an ideal, but everybody should be aware that you will talk with biomaterial scientists from, if you continue working in science, you will talk with them, for many years. And you will see that scientists usually speak only good things about themselves. Why? I don't know. It's a lot to do with a habit. It's a lot to do with their need to attract the funding and to present themselves in the best possible light. But they always tell you that the things are great and we are building things that are wonderful and so forth. But I think that the biomaterial science is at a very rudimentary stage. So we are just starting to uncover and build wonderful biomaterials. And if you look at this picture, you'll see this. I mean, yeah, these are pretty cool things. Tissues, prostheses, cardiac valves, synthetic skin, hip replacements, bone replacements, hernia repair, and so forth. So these are good things, but if you can imagine things, if you read sci-fi novels or whatever, you could probably imagine far greater things than those that we implant in human bodies today. And if you look at the left side of this diagram, this is where we are now. This is one of the materials that is typical, and somewhere in the middle you see the future, like this sci-fi integration of technologies and the human body. And then in some far distant future, we can't even imagine that, right? Maybe we'll become some kind of sublime creatures with the help of some quantum technologies or something. So and we can't even talk about that. But in any case, this is just to give you an idea about the timeline. Now, another possible route, which actually many philosophers of science are thinking about, is this. You start as this curious boy or a girl reading a book, and then you go to this rudimentary stage in biomaterials, the one with the second picture, and they don't have a pointer. Maybe it would be much more convenient. It would prevent the misunderstanding. They do. Oh, wonderful. Okay, so we'll continue before that. So you see the second big picture. That's that rudimentary stage that we are now, and then we go to the third thing, which is kind of like the future, almost like robots instead of people. And then I don't know if you watched the movie Artificial Intelligence. It's a Steven Spielberg movie. I love movies, and I wanted to be a movie director before I became a scientist. And then I realized they enroll only 5 people every 2 years. And without knowing the right person, you could never become a movie director. That was in my home country. So I gave up and I decided to become a scientist. So I don't like Hollywood movies. I absolutely hate Hollywood movies. And this is the only Hollywood movie of the 21st century that I actually really appreciate. It's Steven Spielberg's movie, yes. Actually, it was a collaboration between, thank you so much, between Steven Spielberg and Stanley Kubrick. Yes, and yes, Stanley Kubrick, who directed, yes. Yes, 2001, exactly, yes. So it's a beautiful story about a robot who actually can love, and that's a story about love. It's actually the modern story about Pinocchio. You know, it's again another one of those really beautiful stories. It's here. Oh, it doesn't work on the screen. You know what? I can go there instead.
Cursor, or if you work with the yeah.
Yeah, no, it doesn't show.
work.
I'll get up and I'll show you when I think you could misinterpret. No problem, no problem, no problem. I'll walk. So and actually it's a story about you know, he meets the blue fairy and he discovers that, you know, human, just like Pinocchio discovers, you know, that our human state is actually the most perfect of the states. So using science, we are trying to build something, and actually we're always going to fall back to what we are. So maybe we'll eventually make a full circle, and we'll come back. Thank you. We'll come back and realize that actually we as humans are the most ultimate nanobio machines in the universe, right? Because, you know, that's what we are. And if you read nanobiotech textbooks, they most often, actually very often, adopt that perspective, saying that, you know, the cells and the biology is that ultimate nano device, right? You know, so in trying to build these nanostructures and nanomaterials and nano devices, we can't build anything better and more intelligent than, you know, biology. So I'm offering you to, but so what are the biomaterials? My students often confuse biomaterials with biological materials. Actually, there's a very big difference, because biological materials are materials derived from biology, synthesized by biological systems, as opposed to biomaterials, which are humanly designed materials meant to interfere with the human body, to interact with the human body, to interface with the human body. It does work. It does work. Yes, it just doesn't work on the screen. So when I point at the screen, but no problem. I'll walk and everything is fine. So the history, we know that, you know, back in the history, we were implanting, well, not we, but our distant predecessors. We were implanting very primitive implants, such as glassy eyes, you know, some kind of wooden, also teeth and so forth. So, and then we moved to the 20th century, and the big revolutions were the polymers. And we're going to talk about the polymers, I think, tomorrow. So we came to the PMMA, and it was like most scientific discoveries, it came by accident. There was World War II, and so the pilots suffered from windshields. Yes, so the pierced windshields, and little pieces of that plastic would end up in their eyes. And so it was discovered that actually that particular material, it was a polymetal methacrylate, does not cause any inflammation. And so, so that intrigued the scientists, who went on to actually propose that, hey, you know, maybe we could use this type of material to make it interact with the body. And so, so the polymers started replacing the metals as the predominant materials, and you know, both are only partially successful. And you know, if you're a biomaterial scientist, you should know, or you already know, that there's no perfect biomaterial that works for every single application. For every single target in the body, you need to make a compromise, you know. And so the term biomaterials was coined actually in the 1960s, and in 1975 the society was formed, and nowadays it's a huge field, and you know, it requires input from all kinds of, you know, walks of life and walks of science. Oh, this is my, okay, if this doesn't work, then I'll go back to it. So very often students ask me, are biomaterials and materials in biomedical engineering actually the same? No, they're not. Why? Because biomaterials are the materials that are meant to interact with the human tissues. And materials in biomedical engineering are even materials that are, you know, in devices that are used in the clinic. Okay, so typically, if you were to count materials in biomedical engineering, you would count every single material that is used in technology, right? Because, you know, if you open, you know, electrical circuit, you have just about, you know, everything out there. So biomaterials are definitely a subset within the bigger set of materials in biomedical engineering. There are a few more definitions, you can read about them. And like what is biocompatibility? Biocompatibility is also one of those terms that is often used but very vaguely defined. I don't know if you have taken the philosophy courses in your education, but there's a concept of explanatory principle, which is a principle that you use to explain everything else. But that principle itself is never explained. One of them is energy. Every physicist would be in trouble if you asked them to define what energy is, because you use energy to describe everything else. So biocompatibility is kind of one of those terms where there are multiple ways of evaluating biocompatibility. You can implant a material in the body, or in human body, or in animal, or in different areas of the human body, or in different cells, and you're going to get up just totally different responses. So these are some of the, and so another thing is to be aware of is the feedback loop. Like where we are, where you are, is the education side of this feedback loop, and the next step would be you're getting involved in research and development, right? So you're at this moment you're collecting this great body of knowledge, and then you're going to go out there and going to use that knowledge to build something practical, and that will be the R&D part. And then after you build something practical, you should also be aware that probably 95 or actually 97% of these things never go to never become available to the people, so they stay, buried in some folders in your principal investigator's lab, or they become reported in papers, but they never become actually, they never enter the market in a way. So the third step would be thinking about the commercialization. So that'll be the third step, and finally the clinic. You become, you translate something from a laboratory stage to the clinical stage, where it can become, available to the patients, to people who are in need. Okay, finally, biomaterials for me represents this grand marriage between yin and yang, because again, I repeat what I said, life science on one side, material science on the other. Life science is a soft science, material science is a hard science. Another thing, I think this is the last thing about biomaterials to be aware of, is the trend. And this very nicely illustrates this trend. So biomaterials started off as a sub-discipline of material science. Okay, so material scientists were the first people who were, getting seriously involved in biomaterials research. So at that point, and that was, prior to 1980, so bio was in small letters and materials were in big. Why? Because these people did not know anything about biology, right? They were creating these materials and just supplying the doctors with the materials without any idea on how to test them in vitro or in vivo, or, or actually even thinking about that. They were, at the same time, the idea that the sturdier, the better, was dominating the field. So people used to think that the more durable, the stronger the material, the better it is. And then we realized that's terribly wrong. For example, you have the case of metallic implants as bone replacements. What happens? They have superior mechanical properties compared to natural bone. And so when you have a bone-metal contact, most of the biomechanical force will actually travel through the implant and not through the bone. And so the bone will get resorbed. So in a way, it's telling you that, the stronger, the more superior can actually be more damaging. At that, at point in the 1980s, material scientists started thinking about biology. And so biomaterials became kind of, equilibrated. And after about 2000, bio completely eclipsed materials. So now we know actually that, the complexity of the biological phenomena is so much greater than the complexity of materials phenomena that, we just, we have to start from the biological side, as we often do. So, Another thing, which is the title of this talk, is that, you know, bionanotech is the discipline at the crossroads. And why at the crossroads? Not just that we don't know which way it's going to go, but also that that it's actually at the confluence of all these different fields. And, you know, so biology, pharmacy, physics, medicine, chemistry, these are just some of them, right? There's far more. And in a lecture where we'll talk about nanomedicine, I will give you an even broader example of this. But right now, I think it's important for you to know that you know, you can. This is very good, right? Why is it good? Because you can come from any of these fields, say from physics or pharmacy, and you can enter the biotech, nanotech field. So it gives you a lot of opportunities. So another thing, you know, I'm a physical chemist, and when people ask me why I decided to become a physical chemist, I usually tell them something that I find funny, but you don't have to find it funny. I tell them, well, you know, if someone asks me a physical question, then I can tell them I'm a physical chemist. And if they ask me a chemical question, then I can tell them that I'm a physical chemist. So, you know, so I always have a way to escape from actually knowing the problem. So you always have an escape route, which I think is a good thing, right? So you can always and adopt this what I call a modern approach to science. And that's another thing I want to tell you. You should be aware of that. That, you know, the modern scientist is the scientist entrepreneur. It's not the old romantic school scientist who was very smart, very scientific, very knowledgeable. The most successful scientists of the modern day actually know little about science. They're very good at managing people and picking the right people and actually collaborating and presenting their science to others, which I think is a very big danger, okay? And I think it's wrong in many respects, because I think we still need to be, we need to do our science. But really, that's on, for good or bad, that's where the science is heading to. Another interesting thing about bionanotech is that it's somewhere in between science and engineering. And whenever something is in between science and engineering, you also find yourself in this limbo, because you don't know where you belong to, and that's a big problem. So for science, these are the things that you worry about. You know, you want to be fundamental. You wanna ask and answer fundamental questions. Okay. For engineering approach, you want to be practical. You know, you're not interested in answering why something happens. You don't want to uncover the mechanism, but you want to build things that work better, right? If you know, it's an engineering approach. For science, you ask yourself, is this true? You know, for engineering, you ask yourself, does this work? You know, is this practical? So very often in science, you just worry about the proof of concept, right? And that's what I tell my students in the lab. You know, we are a scientific lab, we're not engineering lab. So in a sense that they need to just prove the concept. You know, they don't need to spend months optimizing a process, because this is not industry, right? So in a way, now the problem is that, you know, whenever you find yourself in that limbo, and you have other people judging your success as a scientist, and these judges will always be inclined to one or the other, you know, so they will often tell you, hey, you are too much of an engineering, you're not really a fundamental scientist. Or the other way around, if you're building great things and you don't worry about asking these fundamental questions, which I think is perfectly okay, there will be people who will come up and say, you know, you're a good engineer, but you're not really a scientist. And so it becomes a big problem when you become a scientist who has to apply for funding. Then, you know, very often to get funding, you have hypothesis. And when you have an engineering approach, what is your hypothesis? You know, there's no hypothesis. There's a hypothesis that says, like, you know, this is going to work better than what other people are bringing. So there's no really, you know, so you're always going to get a bad grade on hypothesis, right? Because they grade your proposals or whatever. So you're going to get like, okay, his hypothesis is very bad. Well, of course, this is an engineering proposal. So this is it. This is basically, you know, so as a bionanotech, you're between biology and engineering. In biology, people want to hear these basic science hypotheses, and in engineering, they want to hear exciting practical ideas. How do you balance the two? There's no recipe for that. I can't give it to you. No one else will. So you have to be kind of innovating. People say think outside of the box or whatever it is, but these are all just very generic advices, right? So so another thing I want to really quickly go through is the prerequisite for a bionic man. Bionic man, which we briefly cover, is that perfect biomaterial tissue compatibility. Okay, so there's no ideal biomaterial, and there's no so don't think that you will ever be able to build something that works for every tissue and for every type of patient. So there's always going to be variation. Say children or diabetic patients will be very, very prone to reject a particular biomaterial, and it will be very, very well accepted by other patients and so forth. So so typically what we do is we tend to substitute like with like. Okay, so if you have a soft tissue, you want to substitute that with a soft material, right? So if you have a skin, you want to do collagen or gelatin or something like that, like a soft material. If you have a hard material such as bone, you want to use something hard, like hydroxyapatite or titanium or bioactive glass. Sorry. So that is, but there are exceptions, as ever, and people say that exception actually proves that the rule is true. So one of the exceptions is titanium stents, right? They actually substitute, they interact with the blood vessels. So they're very hard, as hard of a material as you can think of, and yet they interact with blood vessels, which are a soft material. So whenever you find a rule, there's going to be an exception. So these are some of the examples of traditional biomaterials. You have heart valves, you have artificial hips, you have dental implants, and intraocular lenses. So these are the four most frequently implanted types of biomaterials. You see there, these are the statistics applied in the United States. So about 1 million, 2.5 million, and 100,000 per year for heart valves. So it's really a tremendous number. And let's just very quickly go through some of these biomaterials. We have artificial hips. Then we do artificial knees. We have bone reconstruction, which we will talk more about that. And again, you will have all of that in that pamphlet. Skull reconstruction, which is kind of similar to bone, but a little bit different. You see that the skull is very porous, right? So you want to use something that's strong, but also very, very porous and light. You have these genetic grafts. Dental implants are another common biomaterial. Stents as blood vessel substitutes. There's more complex devices, or it's artificial hearts, which are in a way devices. So they contain more than one biomaterial, and they are made to function in synergy. And artificial skin, breast implants, cochlear implants, intraocular and retinal implants. And this is the example of the first bionic eye that was actually implanted last summer. It's almost like a solar cell of a kind. It's actually transmitting the optical signal from the environment directly to the retina. It's bypassing the photoreceptor cells. So it's not been able to provide a very clear vision, but hazy vision is still better than nothing for patients who are blind. Now there's the question: are these biomaterials too? What do you think? No. Well, no, but then so a biomaterial by definition is something that is interfacing with a tissue, right? So if something is interfacing, like cell phone, yeah, are they interfacing with our skin? I don't know, with our mind. It's hard to say. And for many people who are addicted to cell phones, they probably sooner or later would consider them as biomaterials. They can't live without them, right? So glasses, and so technically the answer is no, but again, it depends on the perspective, right? You can always argue. Like I personally don't like definite answers, so you know, I love those answers that are opening you know, doors to alternative possibilities. Now, so I gave you a little bit of background about biomaterials. Now, so what if nanobiotech is this? What is it's the use of nanotechnologies to control biological systems? So that's one scenario. So these are some of the examples. So you know, they give. So this is pulled from a Sandia National Lab web page. So in a way, this is how they define bionanotech. They define this as biomolecular nanotechnology, actually nanomaterials, nanostructures that are utilizing biomolecules for, you know, who knows what purposes. So this is an example they give. You know, so how do you, have you heard of supercrystals or colloidal crystals as a concept? So crystals are, you know, periodic arrangements of atoms, but colloidal crystals are actually periodic arrangements of particles. And you see some of them, these magenta circles are actually, I believe, gold nanoparticles. And you see the scale is 20 nanometers, so these particles are kind of like 5 nanometer particles approximately. So they are being arranged in a lattice with the help of these biological molecules that are kind of in between them. So in a way, you could utilize these biomolecules to control the symmetry, the arrangement, the organization of these more sophisticated nanostructures. And you know, I don't want to appear like someone sitting here and telling you, you know, we could do this, we could do that. And I've been in your skin, and I've listened to tons of these talks when people say and think like this is something extremely complicated, and they have the knowledge that I do not. And you know, so this is very simple. Okay, so so most of these experiments require just simple precipitation chemistry, which is mixing chemicals, so and depositing them on the surface. So extremely simple chemistry, and that's what I do in my lab. So we stay away from any complicated chemical setups or physical setups. So why? Because we are trying to create something that's biomedical in nature, and if we want to solve the problems that are biomedical in nature, they need to be affordable to everyone. And that's why a great emphasis in my lab is actually on creation of materials that could be made by anyone and using, you know, very cheap resources. So so in this case, this is something very simple. Now this is an opposite example. This is something that's actually requiring quite an expensive setup, and this cannot be made by everyone. So this is an example of a sensor that's actually it's a super fine wave balance. Think of that. Think of all these little these are all like scales, right? So as you put something, they could deflect, and they can measure actually, you know, something like, you know, picogram amounts or even smaller. Why? Because they deflect, and you know, you have the optical signal just being deflected because the lever is, you know, changing the angle. So now how do you what you can do, actually, you can functionalize these little wave balances with biological molecules, and you can provide a specific interaction. So you can put all these things in a solution, and so each of these is going to attract only specific biomolecule. So you would have different biomolecules on each one of them. Okay, so you'll be able actually to measure their amount with a strip, right? You put a strip inside a solution, and it tells you right away how much of anything you have there. That's another example of, you know, bionanotechnology. Again, sensors. This is how, you know, they some of them work. You have, you know, kind of like a layer, and then you have a biosensing domain, which is, you know, made to actually recognize and interact with a particular molecule. In biology, you know, I think 95% of all the experiments are based on specific molecular recognition, right? Kind of like enzyme, key and lock. and stuff like that. That's why how people discovered the pathways and so forth, specific interactions. So it comes natural that in bionanotech, most of the time we use something like that. This is another example. This is just kind of like a fancier picture of what I showed you earlier, that ultra-fine wave balance, kind of like a device to quantify the amounts of molecules in a solution. They call it, this is technically called a cantilever, this kind of lever that's, changing the direction. And they say you can provide like low-cost detectors for biomolecules, such as DNA. There's another example, which is actually more kind of manipulative in a way, in a sense that you could use these ultra-fine nanoscale devices, such as this needle. It's almost like a pen, and you can actually poke the cell, and you can measure, say, if that needle is functionalized with a particular biomolecule that is meant to interact with another biomolecule, you could actually kind of provide, measure concentrations of chemicals and so forth. I apologize for looking mostly in this direction. I don't know why. Maybe I'm right-handed, so I'll try to switch. Well, maybe next hour I'll do the. I'll switch to you. Okay. Or you can even manipulate with organelles in a cell using these nanoscale devices. A lot of these things can happen. So the nanosensors. So this is another example. Again, where the analyte, you have gold. Gold is a particularly common material. One example is the surface enhanced plasmon resonance. I don't know if you heard about that effect. It requires gold nanoparticles or a roughened gold surface that is roughened on the nanoscale. It's a long story. I don't think we have time to cover actually why that is required for this resonance effect. But gold, why is gold good? Because gold could be functionalized very easily with biological molecules using a covalent bond, right? So that's not something that you could achieve with any material. So when you have a covalent bond, it means you can bind. So typically through SH, through disulfide bonds, you go bind other biological molecules. So that's another thing. Say gold nanoparticles functionalized with biomolecules. That's the example of a bionanotech. Guided mode sensors, which would be just kind of like think of surfaces that have patterns which are meant to be optically active. So the patterns would be, so the optical activity is not due to the intrinsic electronic properties of the material, but due to the pattern, due to the topography of the material. Something like the butterfly wings. The butterflies have all these colors on the wings because of that effect, because of the topography effect. So there's no electronic effect there in a way. One example, streptavidin, biotin. You can read about this. I think we have to speed up a little bit. So again, the manipulation of biomolecules. So that is one typical example of nanobiotech. Optical tweezers. I don't know if you heard about them. Kind of like tweezers that you use to to move atoms around. So you have nanofluidics, which you could create very fine channels through which biological molecules could actually flow and made to interact with each other at very fine concentrations. So that's also another kind of nanobiotech application. Now, what about this? What about, I actually even covered that a little bit. So what we've seen in these last couple of slides was the use of nanotechnology to manipulate biology. Okay, but what if it's the other way around? What if nanobiotech is supposed to be the use of biological molecules to actually create new nanomaterials? It would be very cool, and I'm going to show you a few examples of that. And that's quite different, right? Can you put these two things under the same hat, right? Can you hold both nanobiotech? These are very different things, right? So here's one really cool example. This is probably my most favorite example of them all, and it's from 2012. Actually, this group was in Georgia Tech in Atlanta, in the United States. So what they were trying to do, so there were these materials, particular ceramic materials. I think they were germanium oxides, or don't remember the exact composition. But anyway, they would require temperatures of over 1100 or 1200 degrees to be synthesized, right? So clearly there's a large thermal energy barrier, right? You need to provide a lot of thermal energy to create those materials. So what they did, they introduced these constituent ions into phage peptides. Do you know what phage peptides are? They're actually short peptides, like about 12 amino acids, very, very short. So, and there's a library of them. So, macrophages, actually create these very, very short random sequences of 12 amino acids, and then what you do, you put them in a material you want to make, and then you look for those sequences that specifically bind to that material you want to make. And remember, that's a material that can be synthesized only at 1200 degrees. So, and then they figure out, okay, out of hundreds of these amino acid sequences, only these 6 bind very strongly to our material. So they isolate those 6 sequences, and then they actually add the constituent ions to their solutions. And what they observe is that actually at room temperature, their material becomes assembled and made. So that's pretty fascinating, right? And it's just how, I mean, we can't really find a really good chemical explanation for that. But anyway, that's a very powerful example that shows you how great the potential of biological matter is in helping us create more sophisticated nanomaterials, or nanomaterials using, much more eco-friendly methods. There's another example from James Tour lab at Rice University in Houston. So they make these nanocars and other nano devices using organic chemistry. So technically, this is not biological chemistry, but I'm giving you this because it's, it's something similar will sooner or later be made in future, unless it's already made and I haven't been made aware of that. So you have these fullerenes, C60 molecules here, and they are the wheels. And then you have basically just organic chemistry in between, and they can move around. See, these are the little nanocars. So so in a way, you can use organic chemistry to play around and bond all kinds of biomolecules and create these kind of nano machines. Okay, like nanomotors and so forth. So this is another example where you see basically, you can read more about that, but another example where, the DNA is being attached to these polymers, and it's helping actually them assemble into these patterns. So DNA is a very, very frequently used molecule for these applications. Why? Well, we don't know, but we know that aside from its role in actually transmitting and encoding for genetic traits of the organism, it also has very, very powerful self-assembly properties. So you can use DNA to help all these materials assemble into exciting morphologies. This is what they do here. They actually tell us what kinds of, sometimes they're called DNA origami structures. So again, another question that we ask is, what if nanobiotech is just biological systems, as I said, being the ultimate nano devices? And that's what, again, a lot of people, you can find a lot of textbooks where they tell you exactly that. And you think you're going to find something exciting about nanobiotech, but you see another molecular biology textbook, because they just tell you about this, the cell membrane, cell membrane is actually a very fascinating nanostructure. It's fantastic. It's it's organized, and and a lot of these parts of the cell could be considered nanostructures. So, but to me, in a way, it's kind of cheating, right? It's really it's kind of just giving a new name to an old field and then presenting that as something exciting. So this is one thing. This is kind of a reminder for me. So here we've been sitting here for an hour, and I've been telling you all these things. And what is the outcome that you probably have by now? That I don't even know what's nanobiotech, right? So, and not that I do not know, but I don't think anyone knows. And we could actually, and I think that's the fact that we are sitting here and talking about this is in a way telling us the importance of this field. Because anything new that's kind of just popped out of the embryo is going to be like that, right? It's going to create this massive confusion. Like we don't know where it's heading and how it's going to end up and what form it's going to take. But I think in a way it's kind of proving. Now, another thing is that, as it often happens, as we sit and discuss the terminology, right, we forget about the essence. We talk about the surface. And that's often a trap that we tend to fall to, right? And we should try not to have we should try to avoid it at any cost. So so I think what comes next in the next an hour and a half, 2 hours, we're going to talk about the essence, and or actually more in the next days, more essential, more things that actually would help you really utilize that in your lab, and so that you could actually feel like you learned something that you could apply. Because right now what we've been doing is just some kind of mumbo jumbo. I gave you though a little bit of background, but you'll see gradually. I'm a very confused man, like every philosopher, because I think that's a natural stance to adopt when you think about things. Whenever I found people who are very certain about things, I know that they don't know much, because they're repeating whatever they learned. I think the next level of knowledge comes when you start to wonder about these things and realize how actually even those things that you thought were right are, very disputed. And I think, that's what I tell my students, don't be discouraged from, questioning other people, even though those could be the stablest paradigms ever. Question them, and there's nothing. I mean, thermodynamics and all these things are just standing on very shaky grounds when you start to dig deeper. And this is Lao Tse, of course. Whenever we can define something, right, that's not the real thing. So if we sit here and we cannot define nanobiotech, well, it's the real thing. And so this is the last slide before we have a break. So I call, for this erasure of preconceptions. And I hate to categorize, and my students know that because I teach biomaterials, I teach nanoengineering. Whenever there's a categorization, I don't teach about that, because I hate to categorize. It's just, I think it's deadening for students' knowledge, because it's just putting these things in categories. And so this is, do you know from what movie this is? Yes, exactly. Okay. So it's the last part of the trilogy, the famous Apu trilogy, which is considered, I think, the most, at least in the West, it's considered the most famous Indian movie ever made. And there's this particular scene up with this unfortunate man who loses, sister, and then parents, and so forth, and then a wife, and so there's a scene where he's sitting on a top of this mountain, and he's a poet, he's writing, and then he just lets these things just go away, and you see the papers are getting dissipated, they fall down the mountain, and his real journey begins then. It's a very powerful scene. So you should renew your, movie knowledge if you haven't. I very recently watched the movie, and Akira Kurosawa, the Japanese movie director, said, "Yes, Kurosawa, you came at the exact moment. You would think that this is a film history lecture, because we were talking about movies. You went away, you come back. This is again." Yes, me too.
Have you seen the Ikuru?
Ikiru, oh, it's a beautiful movie. Yes, yes, very beautiful.
And then Seven Sunglasses.
Yeah, yeah, but Rashomon is my favorite. So. Yes. Yeah, the last scene where he carries the baby, it's like it's the most powerful. It's a poetry movement. So again, Professor Neogi must be thinking that we were not talking about science here, we're about film history.
This is our Soviet.
Yes, yes, exactly. So I started saying something, but I completely forgot. So my train of thought was disrupted. So yes, Akira Kurosawa said, if you haven't watched this movie, it's like you have never seen a sunrise. So it's very nicely depicting actually how impressed he was with that movie. So I was told that there's a 5-minute break, but so we can 5 minutes remaining. So do we have to talk for the 5 minutes, or we can? Yeah. So we can have a break, and then we'll continue. Sounds good. Yeah. So, I mean, you guys, I mean, you can distribute that later,
Later,
or
we can distribute that later. No, that's not a big
it's
deal.
definitely. So I think we can start because he says when I can start. So I'm gonna tell you about. I think the title is gonna be up soon, so you'll see nanoscience and nanotechnology. So okay. So we talked a little bit about nanobiotech. What is nanobiotech? And we couldn't find any agreement, right? It could be many things. But we concluded in a way that the fact that we cannot really untangle what it is signifies the importance of that field. Now, right now, in the next 1 hour and a half, we're going to talk about nanoscience and nanotechnology. So we're going to forget about bio for a while, or for most part of it, and I'm just going to give you a very detailed and elaborate background. At least that's how I think it is. Now, it's also going to be a very fun talk. So the first time I gave this talk, I believe, was for minority students in San Francisco at one of the city colleges. And that was the old version of the talk. But, the general concept, the general kind of, structure is very similar. So think of this as a talk within a bigger frame of discourse. So again, it's going to be fun. It's going to be more fun than what comes to tomorrow and the day after. So let's slowly go, because there's going to be a lot of material, and you will definitely be tired after this. So this is, I call it time to be so small. And when I started using that phrase, it wasn't, believe it or not, but it wasn't that common. But now everybody, you have these conferences happening on nano, and they call it something like small. This, you got to be small. But so it became this, cliche in a way. So so this is one cartoon that I like. So a visitor comes to his friend's place, and the friend is staring into the telescope. And his wife says, "You see, my husband lives in his very small world." When in fact, he's actually looking at the universe, right? So, so nano is kind of, in a way, very similar, and not just nano, but science in general. I don't know if you read about stories about Winnie the Pooh. It's this bear, and he has this little friend Piglet, and there's wonderful a part when they get stuck in a house, and only Piglet can actually sneak through this hole through the house and call for the help. And before that, Piglet, as an interlude to that story, Piglet is asking Winnie the Pooh, I'm so small and I'll never become anything. And Winnie the Pooh tells him, exactly because you're small, you will become useful in the adventure that is before us. And then they get stuck, and he's the only animal that could escape through that little hole. And and if you look at Isaac Newton, there's this excerpt from one of his books where he compares himself to a boy that is on a seashore, and he's actually just diverting himself now and then by picking a smoother pebble or a seashell. And when the great ocean of truth, he says, lay all undiscovered before me. So again, this science in general is kind of the talent, the art of finding beauty and importance in small things, right? So you can be focused, you can be specialized and focused on the tiniest subject of scientific research, and yet find meanings that are applicable to your life, to your relationships with other people, with anything. So in a way, this Newton's a metaphor reminds me that actually, as scientists, this is what we are. We're kind of, in a way, always standing on the seashore and gazing at the ocean. The shore itself symbolizes the knowledge. This is a firm knowledge, it's solidified, it's kind of already there. It's kind of something that we assume that's being correct. And the sea is this amorphous, unformed knowledge, which we kind of try to make sense of. So kind of like a dreamer on the seashore. And this is an excerpt from Peanuts, from Snoopy. And so, yeah, so they're standing there and they are just lying on this hill, and one of them says, you know, I could just lie here all day and watch them drift by. So that reminds me about the talent that I love to recognize in my students. So I tell this to people and they don't believe me, but I'm never interested in those A students, you know, people who are always overachievers, who are always the best of the best. I try to find my favorite student somewhere in the middle, you know, somewhere in the B to C range. Why? I love students to be lazy a little bit. Why? Because if you go back to the beginnings of the human or our philosophy, at least in the West, okay, I'm making a terrible mistake for telling that this is the beginning of philosophy. It's not, because I'm standing at the place where I'm immediately embarrassed by saying this. But you know, Socrates and the Greek philosophy, they were just a bunch of guys who were sitting under these trees and, you know, kind of wasting their time talking about random things. So they were lazy people, right? They were philosophers. They're totally opposite of the practical Greek people. But that's how the philosophy of the West came to rise. Now, so in a way, you know, I love to see that in students, that you know, kind of sense of getting lost all the time. You know, if I work with people who always know what they want, and that is very common in the West, because people are like little machines, right? They're always, you know, kind of in this logical frame of mind, never questioning themselves, overconfident, especially in the United States. I don't belong there, right? So I love to see students who are coming to me and say, you know, I'm just lost. I'm lost. I don't know where I'm heading to. So this is what happens when you stare for too long at any object. And that's what the cognitive science tells you. If you stare for anything for too long, you become blind, right? Everything else falls into a blind spot. This is what you get. You get a nothing. So if you're always linear, always narrow-minded, always gazing forward, you actually become blind, right? I mean, epistemologically blind, not physically blind. This is my favorite quote that relates to this. So the Kipling, Rudyard Kipling, who spent a lot of time in India, as you must know, said this in one of his poems: "Who knows England? Who only England knows." What he wanted to say, that you can only know England if you leave England, right? So a traveler actually learns about his land by leaving it behind, right? So, so in a way, if you want to learn about your subject of research, you need to go somewhere else. You know, you need to jump into some other field, and that's how you learn about, you know, what's left behind. So in a way, that brings me to the point of the merit of, you know, interdisciplinarity, of you know, hopping from one field to another, and that's what nanobiotech is, right? You must have gotten that by now. You know, this kind of confluence of fields where you never know where you belong. You know, are you here? Are you there? I give you an example of nanobiotech surrounded by nanoscience, biomedicine, biochemistry, molecular biology. It's just, you know, a melting pot of fields, of perspectives, of worldviews. So on one hand, you have the small, beautiful of science. You know, you pick a little pebble. That's what this hand is doing. You pick a little pebble, and it opens the window to the world. On the other hand, you have the interdisciplinarity, right? You know, you're standing on this bridge, nanobiotech. You have life science on one coast and material science on another coast, and you're trying to make sense of it, right? So the beauty of interdisciplinarity, and if you ask me, I would tell you that all the most beautiful things in life come at the crossroads, right? You find yourself at a crossroad, and you don't know where you're going to, because you're at a crossroad, right? You're perplexed, you are lost, but that's the most creative standpoint, okay? And at this stage of your career, I've been there. You know, you're a student, you're at one of those crossroads because you don't know what you are going to become. Life paths are right in front of you, and so it's a very powerful and creative standpoint. Okay, so try to take use of it. You know, so this is where I come from. This is where I was born. This is my hometown, Belgrade. They call it a white city. It sounds very white. I don't know. So it's dirtier than so I don't know who, you know, it doesn't live up to the name. But this is where I was born, somewhere in the city, and the city is known for being actually the biggest confluence of two rivers in Europe. Danube, yes, Danube and Sava. These are the two, and so they dominate. Another thing about Belgrade is that it's always stood on the boundary between cultures. You know, the Roman and the Western Roman Empire and the Byzantine Eastern Roman Empire. The border was running through Belgrade. Later, when the Ottomans came, you know, that was the borderline between the Habsburgs and the Austro-Hungarians and the Ottomans on the other side. So my hometown was actually razed to the ground 44 times, more than any European city. On average, we would have a war waged over Belgrade every 33 years. I've gone through one. My grandma, while she was alive, she's gone through three. My parents through two. So it's you know, it's always been, so I've always been inclined to think from this perspective of, you know, kind of interdisciplinary things, you know, kind of a multitude of things colliding and clashing. So today we know that there's really no boundaries for this interdisciplinary, you know, cross-fertilization. There's really fields of science that you would never think about putting them together, and they are put together. So I give you two examples that I think are very powerful. So one of them is the example where they took a model that was used to predict the nebula formation in stars and applied that model to the brain, and then they realized they could predict the, you know, the aggregation of specific cells. I really forgot which, or glial cells or whatever, in the brain. The same model. And then in turn, there was a model that was actually used in neurological research. And then that model, the exact same mathematical model, astronomers realized they could use it to predict the movement of stars. So, so in a way, you know, there's really no limitation. I could go on and give you more examples of this. Have you heard about this character, the Little Prince? No. So he's the character written by from a book by Antoine Saint-Exupéry, who was a French pilot who died in World War II. And he wrote this beautiful book. This is one of the most beautiful books that I have ever read. It's a very short book. It's about this interstellar traveler. And he's traveling from one planet to another, and on every planet he meets new creatures. In a way, it's a metaphor of you know, how everybody lives on this planet of their own, right? And the Little Prince, this kind of like a sacred character or whatever, he has the courage to actually go from one planet to another because he's curious to see what life looks like from the perspective of another human being. He has this, you know, power called empathy. And so I've been something like that. I give you a little background about myself. I'm a little bit self-centered, but what can I do? So I give you, you know, like Little Prince, I've been also involved in a lot of research. So in a way, I'm justifying this thing. So don't think that I have a good friend who's a surfer and who's an expert in dentin and nothing else. So he says, I want to be an expert in dentin and I want to do all the rest of my spare time surfing. And I think that's fabulous. And I'm a little bit jealous because I could never be like that. So I've been doing research, you know, I've been jumping like every couple of years into a completely new field of science. Why? Because I realized when I'm, you know, relatively young, I could, you know, use that time actually to learn about all these things. And, you know, and then later I can combine them into different things. So you see that I've been working on bone research, colloid chemistry, anti-tumor magnetic particles, cholesterol self-assembly, reverse micelles, and so forth and so forth. You know, I mean, I was in a band too, had a band in Serbia, but it's a long story. I also wrote a lot about science and theology. I also published a bunch of philosophical papers, which I have to hide from my scientific peers because they think I'm not a serious scientist if I write about philosophy. Well, that's what science has become. So nanoscience. Okay, time to go to the real subject after this, you know, fancy introduction. So a lot of people tell you, that nanoscience is this new field, and nanoscience, think of that, it's the background of nanotechnology, right? It's the scientific framework that is helping us build technologies that we call nanotechnology. So let's talk about that scientific framework. Let's be more fundamental. So they tell you, this is science, but actually it's quite a natural progression, and you can see that from this graph. So I created this graph for the purpose of this paper. It was like 6 years ago. So I created this time scale going from the Stone Age to the modern age, and also coupled spatial scale next to it. So what is this spatial scale telling you? It's telling you the critical boundaries of the most sophisticated products of that particular era. So when you were in a Stone Age, this was the most sophisticated product, like some random tool. So what was the critical boundary? Think of that is the length scale that you cannot exceed without that product failing, right? So in a way, if this hut has an edge that is moved by, say, 100 millimeters more or less, it's not going to collapse, right? So that's a critical boundary. As our ability to manipulate the physical matter improved over time, we pushed the scale to ever finer and finer length scales. Okay, so we started building something like knives or swords, and at that point we were already in some kind of millimeter range. Musical instruments, clocks, we were in the micrometer range, the cars, and then naturally, right, we come to the range that is below 100 nanometers, and 100 nanometers is that boundary for nano realm, and we can create these nanomotors, even computers in a way. If you consider semiconductors, nowadays I think the finest one have like the individual P and P could be like 25 nanometers, right? So that's a nanoscale technology. So so in a way, it's a very natural process. And in 2009, this was predicted. By 2015, 2 million scientists will be working in the field of nanoscience. Is that true or not? What do you think? It's actually not measurable anymore, believe it or not. You know why? Because like 10 years ago, when I went to a conference, they were nano symposia. You would go to a material science conference, and let's say out of 30 symposia, you would have, say, 2 or 1 or 2 or 3 on nano something. And then 5 years ago, there was no more nano symposia. Why? Because all of those other fields of material science became nano, right? So nano became everywhere. So it became meaningless to have separate symposium nano when actually so it's in a way, the prophecy that happens to, when something becomes really, when something really wins, as a concept, it pervades everything. Yeah. So we can't even estimate, because there's a lot of people working in a nanoscience field, but are not really explicitly, enlisted as such. So let's go back to the beginning. How did nanoscience come to life? So what was what is nanoscience? Okay. So I believe that at the beginning, at the entrance to each new scientific field, there's a question, there's enigma, there's a sphinx, right? Sphinx asks a question, and the questioner doesn't know how to respond. So at the beginning of nanoscience, there's a question, and this is the question. So it's summed up in this graph. I know I'm not explicating this really well. I'm not explicating in words, so I'm going to tell you. So for a lot of physical properties, you could extrapolate them using the particle size in a material. So particle size, think of that. Most materials are polycrystalline, like this table, or this cell phone. It contains particles that are, if they are smaller than 100 nanometers, they will be considered nano. So you can extrapolate a lot of these properties by knowing the particle size. So if you go from 100 micrometers, go down, and once you hit the 100 nanometers, typically the dashed line would be the extrapolation. But what you see in reality is the deviation. So the theory deviates from the the experiments. So we realized that actually the behavior of the material, of nanomaterials, becomes vastly different from their microscale counterparts when you hit this boundary below 100 nanometers. And that is what sparked the interest in nanomaterials. So we realized, okay, we have these nanomaterials, they behave very strange, right? We can't really predict their properties. And I'm going to give you a bunch of examples right now, because they might be instructive. If not now, then later you can go back to this and read more. So one of the oldest examples is the hole patch relation. So hole patch relation is actually relating the yield strength of the material, so the strength at which the material starts to deform plastically, to the particle size. And you can say that actually the bigger the particle size, the smaller the yield strength. So in a way, it's telling you that if you reduce the particle size, you are reducing the chance that the crack will propagate in a way. So you are reducing the, you go from this material, kind of ideal monocrystalline material to polycrystalline material, and as you multiply the number of grain boundaries, you're actually increasing the strength of the material. Now, what happens is that, so this would be the ideal hole patch relationship. So in the ideal case, you actually, so you follow this very well up to certain grain size, and if you go below that grain size, you have a significant drop. So you have a completely opposite effect. It's called the inverse hole patch region. So actually, in that range, the material becomes weaker, right? If you keep on decreasing the particle size. So that was one of the first wake-up calls for scientists when they realized, hey, hole patch relationship fails for nanomaterials. Like, what do we do now? Like, do we need a new theoretical framework to actually describe the behavior of these materials? At that point, it was really too early, But then, once these examples started multiplying, then slowly, typically physicists or physical chemists started saying, maybe we should think of a general theoretical framework that would actually explain these materials and why they behave differently. So again, we're going to go through multiple examples right now. This is another example. So the melting point of materials. Okay, I'll give my promise. Switch to the other side. And my neck is better. It's better. So I can switch to this side. So again, but this doesn't work. So I'll go. So if you look at the melting point of the bulk material, so the bulk material means the material with like very large particle size, so micrometer size, and you drop the size to 20 nanometers, you see a drop in melting point. Okay, and then if you drop it even more to 8 nanometers, the melting point drops even further. So one of the ways to explain that is that the surface area is increasing. So actually, if you deliver the heat, if you have an increased surface area, there's going to be a bigger contact with the heat. So another example is here something we often see with nanomaterials, that the method of synthesis is greatly determining their properties. So you see identical material. This is indium, and you see this is the dependence of the melting point as a function of the particle size. And you see a completely different curves, right? In this case, it's increasing, and in this case, it's decreasing, right? And what is the difference? They were made by two different techniques. So how do we explain that? A mystery, right? I'm piling up a lot of these mysteries now ahead of you. Now, what is this? Another thing that's very important here to notice is that actually a difference between the bulk, say, 100 micron particle size, and a 20 nanometer particle size. So the difference between 8 and 20 is actually bigger than 20 and micro, right? So that tells you that this tiny difference in the particle size in the nanoscale can be more significant than this huge difference in the particle size, right? And that's what we often see. People compare, say, 5 nanometer particles and 7 nanometer particles, and they say, like, wow, they are totally different. Like, why? Who knows? So phase diagrams, if you open, I don't know, are there any material scientists? There must be material science, or at least you had material science courses. So you covered phase diagrams. So what they give you as phase diagrams in textbooks, they never tell you they're particle size dependent, right? But they are. They are very particle size dependent. So this in black would be the general phase diagram you see in a textbook. But all these changes occur. This would be, the blue would be actually the 54 nanometer, and the red would be the 32 nanometer particle size. So, so whatever they tell you in textbooks, well, let's be aware that there are some, conditions under which that works. So bond stiffness, bond stiffness is also subject to a sudden decrease after about at below 10 nanometers. Optical properties, this is one of the examples that you might have seen, that you see the gold spheres and gold nanoprisms. So the different particle size, 40, 80, 120 nanometers, you see completely different optical properties. For those of you who want to know more, it's about the band gap, right? So you can actually change, you can tune the band gap with the particle size, and the band gap is determining the frequency of the light that is emitted as the electrons hop from the valence band from the conduction band to the valence band, right? So the capacitance of carbon, another example, increases as the material is decreased below 1 nanometer. Another example from the literature, again, the particle shapes, changes. So the metals can become insulators, right? That's very interesting. Why? Because the electron free path becomes reduced, and so when you have a lot of when the particles are very small, when they're nano-sized, you have a lot of what? A lot of grain boundaries, right? So a lot of disordered surface, and so when the particles are very small, right, the electron has a hard time hopping from one particle to another, because all these are like, very, very.
Is this known as quantum confinement?
Yes, it's one of the quantum confinement effects. Yeah. So so in a way, I mean, another quantum confinement is actually the band gap that I mentioned, where you kind of, when you decrease the particle size, you are in a way creating this ocean of forbidden zones around single quantum states, right? So the smaller the particle size, the broader that space. So that's why the word confinement. So the quantum states become kind of more isolated, right? And in a regular material, as some of you might know, the quantum states are forming bands, right? So multiple states. So actually, that band is kind of a singular state for so you don't have isolated states as in individual atoms, right? But when the number of these atoms that form a particle is reduced below, a certain number, then that discreteness start to appear again. So you no longer have bands, but you have actually discrete, spaces and discrete states. So so that's quite interesting. Again, so some metals become insulators. Okay, this is it. And you can see on the left dependence on the particle size. So this is the resistivity. You actually see that the resistivity is very low for 60 nanometer, and it goes higher and higher and higher. For 5 nanometer, it's very high. So resistivity inversely proportional to conductivity. Another effect is when actually isolators become conductive, and that's also another weird effect. So isolators can become conductive. Typically, that happens in oxide conductors, so not in regular. So those that actually, for which oxides can, act as ion conductors. So ferromagnets can become super paramagnetic or paramagnetic, which is, super paramagnetism is some kind of, in between. So the material is behaving as a ferromagnet in the magnetic field, but once you remove the magnetic field, it actually turns into paramagnetic state. So it's actually a paramagnetic. So it's kind of in between the two. You see that here on the left side, see as the average particle size is decreasing, the magnetization is dropping. So actually the average particle size, and you see this is the remanence. The remanence is, dropping, as the particle size is changing. So the remanence is the indicative of superparamagnetism, right? Superparamagnetic materials have zero remanence. Okay. And there's an example of some paramagnets that become ferromagnetic, actually. That's below. This is very uncommon, but it does happen. Now, biological effects. Body really responds completely differently to materials. And so this is one example here. I can stand there. So for some materials, there's no difference, right? So you have, iron oxide. So the light gray would be nanoparticles, and dark would be the regular particles. No particular difference. And then you see for some of them, there's a significant difference. Copper oxide, you see that actually nanoparticles are much more toxic. The percentage of depolarized cells is much higher for these nanoparticles than for micrometer particles. So again, so this is what we see often. This is a particular polymeric particle for 20 nanometer. They would be toxic for 130 nanometer, just totally fine. And then for other materials, you see a completely opposite effect. So for these cerium oxide particles are actually, when they are small, they're harmless. But when they are bigger, when they come into contact with a cell as aggregates, they become much more toxic. For nanohydroxyapatite, we see actually, kind of a similar effect. This is very, very strange, that actually at a smaller concentration, they're more toxic than at a higher. Why? Nobody knows. But sometimes in this case, the idea is that when you have a higher concentration, they agglomerate, and they kind of don't have that toxic power. So the drug loading capacity, if you compare how much drug you can load in a particle, it's also much higher for smaller particles, right? Because the specific surface area is bigger. So if you compare 5 nanometer particles and 100 nanometer particles, clearly 5 would load more. The catalytic properties, again, another consequence of the specific surface area. So you decrease the particle size, you increase the specific surface area. The surface to volume ratio becomes much higher. So you have more surface to interact with whatever it interacts. So if the surface is catalytic, it's going to be more active. That's the example of gold, right? Gold is a perfectly inert material, but when it comes to nanostate, is actually a very powerful catalyst. So another, paradigmatic example. Now I give a whole class at University of Illinois that is actually just on this, just on this. So we spend the whole semester discussing the physics and chemistry behind the, nanoscale phenomena. And why nanoscience is so complex. So technically, these are two effects at work. I think you should know that, at least. So on one hand, you have the surface effect, which is a classical physics effect. That is the consequence of the fact that as you decrease the particle size, more and more atoms are going to be on the surface, right? So for this big of a particle, you have, 60% of the atoms on the surface. And if you have this big of a particle, you see 100% is on the surface. So all of them. And surface atoms are far more interactive, right? They are disordered. Surface is, curved. It's disordered. It's undersaturated. The bonds are undersaturated. So there's a surface tension. The surface is pulling inside. So it's more kind of energetically, it's more prone to interact, right? It has, it's in a higher energy state compared to the rest of the material. And then the second effect is quantum in nature. That's the quantum confinement that you mentioned. And, the fact that actually, you have the discretization of states as you confine. So actually the small particles could be modeled as quantum, entities in a way. So, so one of the difficulties in this is because when it comes to describing nanomaterials and nanoscience, we don't know. Another problem with the language. We don't know what language is more appropriate. Shall we use classical physics language or shall we use quantum language? So sometimes one of the is more appropriate than the other, and sometimes it's the other way around. So so that's one of the regular problems. So nanoscience is also prone to what is known as the butterfly effect. Do you know what the butterfly effect is? It comes from the chaos theory. So Edward Lawrence was what's it called, not a climatologist, but the weather pattern scientist anyway. So he was modeling this weather pattern, and so he made this deterministic model, and he realized if he changes the input values by a very, very small amount, it would have tremendous consequences on the outcomes. So he compared that with a metaphor saying that basically this difference in the initial conditions is so small that that it's compared to the butterfly flaps in Tokyo that could cause a tornado in Texas. So in a way, so when it comes to making nanomaterials, this is what we often see. We see very unpredictable morphologies. And not only that, but we see something that's highly irreproducible. So why? Because we have reached the limits of our ability to, control the materials when it comes to the nanoscale. So these features of the materials are just so fine that at that point we're just, what we get today, we do not necessarily will be able to reproduce that tomorrow. So this is one example from my research. So another coming here that illustrates the sensitivity to external conditions. So if you run these chemical reactions in a closed vessel, you'll get this. If you run it in an open vessel, you get a completely different morphology. And that's something you see regularly when it comes to the making of the nanoparticles. A bunch of these examples exist. Here on the bottom you substitute manganese with nickel, and you get spheres, so you get needles. So you have a bunch of these examples. This should be playing. Okay, it's playing. So here we have two examples. One of them is stirred, and the other one is not stirred. These are gold nanoparticles. So basically, it should be different. I even forgot what is. Let's try to play it again. I think it's yeah. So let's go forward. So another thing is that, as I say, like in a good detective story, the neglected factors is one example from reverse micelles. So so they couldn't figure out. If you go to this paper, you can read more about this. But they were trying to figure out actually what's causing the precipitation of these calcite nanoparticles inside of these structures called reverse micelles. And they realized it's the bubbles. It's the bubbles. It's carbon dioxide bubbles that are actually getting entrapped along the edges of these reverse micelles. Now we know that actually a lot of these effects have tremendous influence of nanoparticles. Ferrioxides are, for example, being formed as a result of these, oxidation processes that happen in the air, right? Due to the air bubbles, or carbon monoxide bubbles, whatever is dissolved in the water. The cosmic radiation, is also affecting the processes. Believe it or not, gravity. Oftentimes we were thought that actually gravity should have no effect on precipitation chemistry, but now we know that's not the case. So if you, there was a study where they not recently, a couple of years, but maybe 10 years ago, they did precipitation of a compound in zero gravity conditions on a space shuttle. So, and the properties were completely different. Why? Because, the convection is very different, and supersaturation is convection driven, right? So so you have very, very different conditions without gravity and with the gravity. So a lot of these things are affecting the processes, and I give you one more example, which is zeta potential. Zeta potential is actually the surface charge, indicative of the surface charge of the particles. So in this case, you have two types of particles that are both negatively charged, and yet they attract each other very well. So you have these weight-shaped particles. Oops. Bless you. So you have the big particles. These are aluminosilicate particles, and you have the little circles, which are gold nanoparticles. And so they couldn't figure out why this is happening until they realized that these particles, the little particles, are actually absorbing exclusively on the edges, and edges would be positively charged, even though the entire big particle as a whole would be negatively charged. The edge itself would be positively charged. So so you know, this is, so all these things, like, they don't tell you that. If you read a book about nanoscience, they don't tell you these issues, because these are all issues that are causing problems to scientists, right? And they want to hide those things because they want to be those guys that are making everything, and everything works all the time. Well, that's not really true. I think it's very important to outline all these things that are the gaps in our knowledge, right? And I think it's important for you to know, because that's how, you know, you will be able to find places where you could fill those gaps, right? I think that's the first process in the evolution of new knowledge, being aware of the gaps, right? And once you're aware of the gap, you can think about a solution. So this is, I show you this, you know, popular singer. I don't listen to her music, don't think about that, but I like the picture because she's keeping one eye closed. And that's a common problem today. I think they call the year 2001 as the year of retractions, because so much scientific data today you find in the literature are just being, you know, it was fabricated. Why? Because there's a huge pressure to publish, and people know that they're going to lose their jobs, or they won't get their PhD degrees or whatever. So we live in this ultra competitive world of science, and people are just ready to do anything. So this is the number of retractions. You see, it's kind of increasing constantly. So the papers are getting retracted because the scientists are, you know, think that it's okay to turn a blind eye on some data, right? Not necessarily, on most cases, probably to fabricate completely, you know, data, but at least to say, okay, this was an outlier. Well, I don't know if it was an outlier, but, you know, but I'll treat it that way. So that's something to be aware of. I think we can go, like, we have 54 minutes. So I think we'll have enough time to go through that. But if you're tired, let me know, because I know that, you know, this is going to be a lot of material piled on you. And so I'm going to give you a couple of advices when it comes to synthesis of nanomaterials. Okay, so if you want to be the one making nanoparticles, nanostructures, these are the advices that I'm giving to you. So we're going to go, like, slowly. The first one is this, you know, kind of stand in the middle of the ground between top down and bottom up. So let's see what top down and bottom up are in the world of, you know, nanoscience. So first of all, it was about 10 years ago when this battle was raging in the nano world. The battle meaning the clash between two opinions. So one of them was Eric Drexler. He was a proponent of the idea of molecular assembly, that actually everything could be synthesized using these highly manipulative technologies. You have seen those IBM logos, you know, IBM spelled with xenon atoms. Yes, with xenon atoms. So something like that, where they basically picked, you know, individual atoms and arranged them. So that was the idea behind that molecular assembly. And opposing that idea was Richard Smalley, who was the Nobel laureate from Rice University. And he was saying, no, we cannot build anything using anything. And we need to let nature help us assemble things. So if you compare these two perspectives, you realize the first one is very anthropocentric. Like, you know, we're gonna build anything. We're gonna build these devices atom by atom, and you know, they're gonna stay there because that's how we want. But the other approach is much more organic in a way. So it's telling us that actually we have to assemble new materials, new nanostructures together with nature. That type of approach is called self-assembly. Self-assembly means that you are letting something self-assemble. You know, so you're letting the natural propensities of these materials guide you and guide the evolution of these structures into these morphologies. So you see Francis Bacon, I think, very nicely describes that. Nature to be commanded must be obeyed. And so, yes, using the former techniques, you can build something like this mini Lisa. So she's not Mona Lisa, she's mini Lisa, because she was imprinted on a 30 micrometer. So it's kind of like the tip of the, smaller than the tip of the needle. So yeah, that's something you can build using self-assembly, because nature is not interested in, you know, building Mona Lisas. But using self-assembly, you can create something like this, very finely organized and large, you know, very large quantities of these, you know, self-assemblies of, you know, gold nanoparticles, for example, as here. So, so the idea is, you know, we should think about in the direction, and people are already doing that, in the direction of combining the two. Combining the two so that we can compensate the weaknesses. You know, so if you talk about top-down, what is the good thing about top-down? Because you can very precisely manipulate these things. What is the weakness? The methods are very expensive. They're very time-consuming. How long does it take to build a structure using atom by atom? It takes forever. And what are the good things about the bottom-up, the self-assembly? The good thing is that you can have very large yields using very simple, you know, ecological, eco-efficient methods. But what is the bad side? You have a very weak ability to integrate those products into something functional, right? So if you combine these two approaches, you can actually, you know, get a good. So one of the big problems, and you can see that from this, you know, pie here, that if you look at the biggest share in the patents in, you know, in nanotechnology, it's still nanomaterials. It's still nanomaterials, not nano devices. So what is that telling you? It's telling you actually that we create these materials in forms such as powders, particles, but we do not have the knowledge on how to actually integrate them into something functional. So by just looking at this pie, and nobody told me that, but I looked at this pie, and that comes very, very self-explanatory. And actually use, you know, nanomaterials are most research. You see nanoparticles, you know, are actually most done research on. You see the same here, you know, nanoparticles are leading. So the thing is that, you know, in order to translate these nanomaterials into, you know, nano devices, we need to have them coupled to something where they could be integrated. So some methods, such as lithography, or, you know, something even more sophisticated, you know, optical tweezers or microfluidics, you know, something like, you know, more. So one of the things you could do is, you know, you can create a middle way, and this is what people work on. So they provide a middle way between lithography, which is very top-down, which is the epitome of the top-down method, where you can, you know, kind of literally, you know, lithographically determine the pattern, with the self-assembly. So, you know, you can control the properties of the materials using two parameters: deposition flux and diffusion rate. So if your deposition flux is very high, you do not leave enough freedom for these entities to move around, to diffuse, and to actually, you know, self-assemble. But if this is very low and this is very high, you know, then actually you give them that freedom. So it depends on what structure you want to build. You know, if you want to have very rigid structural features, you want to minimize the self-assembly aspect. But if you want to create something the opposite, like if you work with soft materials, then you do the other way around. Okay, another thing is the marriage of nano and bio, and we already covered that. and I will skip very briefly to that. You know, nanomedicines. So, okay, let me talk a little bit about that. So speaking of movies, I really love, and I didn't like Jean-Luc Godard when I was younger, but as I grew older, I realized how actually great of a filmmaker is. So he was an anarchist, you know, philosophically, and I very much share his, you know, political views. I mean, so he created these new movies that were actually, you know, really, I wouldn't say chaotic, but they didn't have a concept, no beginning, no end. So I think my talk resembles that. So you're getting a lot of these things left and right, and yet I will try to wrap that towards the end. So nanomedicine. So what I work a lot in my lab are these tunable drug release agents. So so what we try to do, this is one of the really important and popular, you know, kind of nanobiotech approaches, to create nanoparticles that are releasing the drugs at very, very precise time scale. So what is drug delivery? Drug delivery is basically the concept that is, you know, building on the idea that it's not, as I say, it's not what, it's how actually that's actually more important than what. So we have a lot of drugs today that we know are potent, but we don't know how to deliver them, right? Take insulin. I mean, insulin is a powerful drug, but patients want to take the pill. You can't give them the pill because insulin is just too big and too sensitive to go through the guts. It cannot pass through the, you know, intestinal, you know, tight junction. Yeah. So drug delivery carriers are needed in that case. Take the example of chemotherapeutic drugs. You know, they are very, very powerful against cancer, but they poison the rest of the body. So so cholesterol is one example. People talk about good and bad cholesterol. There's no good and bad cholesterol. There's only one cholesterol. But what makes cholesterol good or bad is actually the type of lipoprotein complexes that are carrying cholesterol through the blood. So if they're high density, they call it good. If they're low density, they call it bad. So the same is here, right? If you have a good drug delivery carrier, it can make drug good or bad, right? So the drug delivery carrier determines the quality of the drug in a way. And that is where, you know, does it make sense? This is what I often give to students to illustrate that how matters as much as what. So what do you see on the left arrow? What color? And what do you see on the right? What do you see in the right arrow? Blue. So left is green, right is blue. Actually, it's the same color. You can, yeah, if you magnify, even here, it looks like the left is green and this is blue. But if you really magnify, and you can do that at home, you realize this is the same color. So so it's actually just superimposed on a different pattern. So, and the same happens in the drug delivery case. So if you have a nanoparticle as the drug delivery agent, if it was designed well, it can turn drug from blue to green or green to blue. So, okay. You know, why do we need that? Because, you know, I think we are running out of time. So do you want me to go through this really quickly? You know, so I think it's important to you because this is still a nanobiotech class. So we do, so it's important to know, and I mentioned that different tissues require different ideal biomaterials, right? You know, for example, the identity of the drug, you know, you have different types of drugs. Antibiotics are usually divided to two types. So one of them are concentration dependent. The other types are the time dependent. So for concentration dependent, you want to deliver them in a very high concentration manner so as to exceed the minimal inhibitory concentration. For time-dependent antibiotics, you want to extend their release, right? So depending on what the drug there is, you want to have different drug delivery carrier, right? So you can't say, we developed this material and it's going to work with all the drugs. No, that's nonsense. So another thing is that the pathology could be very different. So you can have bone cancer, which is very pervasive, right? Because each of these cells is surrounded by this niche that is actually, kind of supporting their, proliferation, as opposed to bone infection, which is kind of advancing frontally. So it's much more easier to isolate in a way. Again, it's different. It's more difficult to reach sometimes because of the biofilm and so forth, but that's a different thing. And then the targeted tissue, if you look at a bone itself, the inside of the bone is very vascularized. So whatever you release there, it's going to be very quickly, spread by the bloodstream. And if you talk about teeth or the outside of the bone, the cortical part, it's definitely less vascularized. So the location in the body is going to determine. So that's why we need different drug delivery carriers. I'm showing you a part of my research because that's something. So this is something that we delivered. I mentioned insulin, and insulin is very critical to be delivered orally, right? Because the patients want to have them delivered orally. So what we designed was these silicon nanospheres. Oh, actually, I'm sorry, these are microspheres. I apologize. But what happens, we actually grew using the chemical vapor deposition nanowires on their surface. And so those nanowires, and we kind of entangled the drug, insulin or other model drugs, in between these nanowires. So what happens with these nanowires, when they are swallowed, they go to the intestines and they tangle with these microvilli extensions on the cells. So once they tangle, so this would be one monolayer of cells, and these would be particles. So the idea is that so this would be the cross-section, so the blue would be the cell nucleus, and the red would be the tight junction around the cells. So the idea is that these needles would kind of open the space between the cells and let the drug go through. While at the same time, do not damage these things, okay? Because you don't want to induce permanent damage. And that's always a challenge with good drug delivery carriers, how to induce just enough damage to the body for that damage to be therapeutic. That's what people often forget. They think the therapeutic is always kind of 100% harmless. No, the point is actually to be harmful up to that point where actually that harmful effect is, reversible, and therapy is actually enabled. And if you look at the permeation of the drug, you can see that it's increasing when you increase the amount of these nanowires, the drug goes through. Okay, let's go through that. I'll talk about this later. So we'll skip this for now. We'll go back another day. So this brings me to the point that actually another third point that you should be aware of. Oftentimes when you design particles, you would tend to think that chemistry is the most important thing. Okay, that's what people think. Okay, we need this composition. We are going to build gold, or we're going to build silver nanoparticles, or platinum, or whatever. But actually, morphology is equally crucial. Morphology means shape, right? Particle shape. So you have an example of red blood cells. Actually, they can very, very swiftly diffuse through tissues, in part because of their shape. Unlike bigger, or even smaller, spherical particles. So that's another part of research that actually adds up to what I just showed you, the insulin and the nanowires. So another part of that research was our questioning whether, so those basic particles were spherical, remember, silicon spheres. So in this case, we were thinking, okay, what's going to happen if they're planar? So they're spherical here. So some drug goes through, but what happens if they're planar? They change the morphology. Is there going to be more drug? So we wanted to test it out. And so we were also thinking about actually not just using regular planar particles, So not using just the regular planar particles, but using irregular shape particles. Why? Because this is how a nature-made structure looks like. It's very asymmetric, right? And this is how man-made structure looks like. It's symmetric, right? I think we overvalue symmetry, and basically these are the two types of particles that we compared. So these would be the spherical ones, so these would be regular shaped ones. If you send this to a scientific journal today, they would love this. They would want to put this on the front page. If you send them this, they're going to hate it. They say these are not pretty particles. And yet we wanted to show you that these are better. So we wanted to prove them wrong. And we did. So you can see the permeation of insulin across the monolayer of cells in vitro. So these would be the spherical particles, and these would be the P. The P would be the planar up on top, and W means they are functionalized with nanowires. So they will have nanowires on the surface. So we lived in California, and so there was this orange tree. There was a very mysterious orange tree. So my wife's parents lived there, and so they would every January they would bring oranges, and they looked so ugly, but they were like the sweetest oranges I ever tried. And so I decided to photograph them, and so here, and these were the supermarket oranges, and but I unfortunately I don't have them with me, so I can't. I would love, but the point is that sometimes things that are very ugly on the surface, asymmetrical, are actually much more functional. At the end, if you go back to the beginnings of the universe as we know it, if that beginning was symmetrical, if these protons or the primordial matter disturbs uniformly everywhere, no stars would ever form, right? So that distribution had to be, so the symmetry had to be broken, right? And that has to be distributed somehow so that stars could form. So we would not be here if the Big Bang was uniform, if there ever was a Big Bang. So no stars and no life. One really cool example I want to show you. So Warren McCulloch, he was a computer scientist. He said this, that life is a reliable outcome made of unreliable components. And so should be computation. So I figured, like, can this be applied to nanomaterials too? Like, are we supposed to start building materials that are going to be asymmetric and functionally asymmetric? I think I'll show you more about that in 2 days. But right now, this is an example from Dolby et al. It's a group in Ireland. So they seeded cells on this pattern, and they seeded cells on this asymmetric random pattern. And they were looking for the expression of green. Green would be, these would be the mesenchymal stem cells. And they were looking for their potential differentiation into bone cells. And green would be the osteocalcin. That is one of the proteins that is expressed by bone cells. And they realized once they see the cells without any chemical factors, they would spontaneously differentiate into osteoblastic lineage. And how, why, don't ask them, don't ask me. Well, this is a part of our research, but actually I'm going to talk about that on another day. So this is a quote from Igor Stravinsky, the composer, who said to be perfectly symmetrical is to be perfectly dead. And the Japanese art of ikebana is, right, proving that it's all about creating this symmetry, asymmetry that is, if you go back to science, and this is what also is probably the most important thing, all the scientific things you can read in a textbook, but it's very important to be different, right? To be, to question the things and to be asymmetrical, right? To go against the stream. And otherwise the science would never evolve. Nothing would evolve because everything would just confirm what was being used in the past. And Albert Einstein, there was a student, proposing ideas to Albert Einstein. I don't know about this, if you know about this, but he proposed some ideas. probably for his PhD thesis, and Einstein was sitting there listening, and he said, I like your idea a lot, but it's not crazy enough. You know, so that's, you know, has to be okay. I like this picture. It's kind of demonstrating what the recipe for creativity is, at least in my universe. I think it's important that we respect the tradition, because that's the ground of, you know, our work. You know, other people created everything that is around us, but we have to balance that with a very healthy dose of questioning that tradition and, you know, going beyond that. Okay, so, and that is the ultimate challenge: how to love our tradition, but how at the same time to you know, go beyond that. You know, again, no recipe for that either. So composition could be used as a parameter. That is something, you know, I mentioned that chemistry is important, but what people often foresee is that, you know, the chemistry is tunable, right? Very often, you know, you don't have to have a fixed composition of a particle. You can actually have a tunable composition. So, so I'll skip this and I'll go through these particles. So this is a part of my PhD research, actually. So quite a long time ago, 2000. Well, not that long ago. But so what I decided to do, so we wanted to use these manganites because we wanted to test the idea that their magnetic properties would be tunable depending on the composition. So if you have X in that formula, so see X up there, and so if you change X from, say, you know, 0 to 0.16 to 0.5, you change the magnetization versus temperature curves. You plot the first derivative, and then you get the minimum. That will be Curie point, the point at which the temperature at which material loses magnetic properties. You see that actually that temperature becomes directly dependent on the parameter X. And so it becomes tunable in this range from 25 to all the way to 100 degrees. Now, what happens with cancer cells? So the cancer cells are very specific in a sense that they're very temperature sensitive. So at 40 degrees, you could start killing cancer cells, while, you know, given a relatively short dosage, the healthy cells would survive. That's at least the idea. I doubt that that is the case 100% of the time. So people usually use hyperthermia treatments using iron nanoparticles. But the problem with iron is that it doesn't have you can't set the Curie point at 40 degrees. Because once you set the Curie point at 40 degrees, you prevent the overheating of the surrounding tissue. So in a way, if you use iron, you're going to kill the cancer cells, but you're going to kill all the surrounding cells, right? So, so you could actually, you know, and then what you can do, because lanthanum, strontium, manganese not very biocompatible, right? So you can coat these particles with a layer of silica to create a biocompatible layer without actually losing the magnetic properties. There's another way of doing this, and I'm going to show you that actually in 2 days. So forget about this for now. So another thing is the reaction environment is as important as the reaction run. I think we're going to have 12 principles, and I believe we will have enough time. So what I give up there in those little letters below 5, it says lector si momentum require circumspice. I don't think anyone knows where that is from. So if you ever have a chance to go to Europe, and then you go to London, and then in London you go to St. Paul's Cathedral, probably the most famous church in London. And if you go inside that church, you'll see that. You'll actually see the tomb of Christopher Wren, who designed that cathedral. And instead of the epitaph on that tomb, it says here. It says, if you translate this from Latin, it says, "Reader, if you're looking for an epitaph, look around you." So basically it's saying, I'm not here, I'm here. I created this work. So I'm kind of, you know, I'm in the environment. I'm not in here. I'm not in the system. So if you apply that to reactions that are, you know, used to create nanomaterials, you come to a very important principle that people often neglect, and that is that actually the environment is often engaged in controlling these processes. So people often do not report whether they ran a reaction in a plastic tube or a glass test tube, but that's incredibly important. So, you know, because these are completely different environments, you know. So that's just one example. So here is one of them. If you fold proteins, you know, or as example of a biomolecule, and if you put them in oil and in water, their folding is going to be completely different, right? So typically they tell you in textbooks, proteins fold this way, but they never tell you that, yes, they do also in water, right? Because that's the natural environment. So this will be the mean area buried upon folding, so it's kind of changing, and the hydrophobic residues. So basically what happens in water, as the protein folds, the hydrophilic residues are going to be exposed to water, and the hydrophobic are going to be buried inside. And if you fold everything in oil, it's going to be the other way around, right? The hydrophobic ones are going to be on the surface, and the hydrophilic would tend to be buried inside. You get a completely different structure. Again, reverse micelles, there's some kind of nanostructured water pools. You might have heard about them, might not, but they're on the left. So you change the size of these using parameter W, you change the size, and then you change the properties of these. Actually, I did, you know, a lot of work on these reverse micelles. So this is how they look. These are phase diagrams. And so you can actually make very cool nanoparticles inside of them. What is the principle? The principle is that actually once you run a chemical reaction inside of this, and if you precipitate a particle, the size of the particle is going to be limited by the size of this water pool. And you can control the size of the water pool using the concentration of the surfactant. These are surfactant molecules and water. Extremely simple, and yet extremely powerful. So you can play around. You change parameter W, which is indicative of the micelle size, and you change the particle size. And then, you know, you get all these things. But the problem is that, I was working on that, and then I realized, you know, hey, you know, you create a material, and it's going to be very much different. So this is the X-ray pattern of a material. I think this is in the micelle, and this is outside of the micelle. So, so actually, the reaction inside and the reaction outside is completely different. It's giving a different product, right? So, so in a way, you know, you get this kind of feedback loop. It's telling you that the crystallization process going inside a reverse micelle is going to be feedback loop with disordering of surfactant assemblies. So, and then actually in 2008, I managed to publish this picture in a scientific paper. Can you believe that? And I was paid $100 for that. Can you believe that? So back then, that I didn't even know that the journal where I published actually was paying the authors. I think it should be really that way, because now they have this open access thing where actually they make authors pay for publishing, which I think is ridiculous. Because, you know, I mean, you have this concept where these middlemen, which are the publishing houses, are making money. Actually, the American chemical industry, 90% of the revenue of the American chemical industry comes from the publications. You know, I'm sorry, American Chemical Society, not American Chemical Industry. Yeah, that would be so ACS. Yeah. So and you know, they're neither the creators of the published nor they're the consumers. So a typical middleman, right? Kind of like the American healthcare insurers. Well, tells you what I think. We're recording this. We are recording, but I could be held eligible in the United States, where I'm not right now, so I can say anything. Okay. So so any case, so this is because of this concept that you know, who's controlling whom? Like if you have an acrobat juggling oranges, is the acrobat controlling the oranges? Because he's limiting their freedom, right, of options of movement. But these oranges are actually limiting the acrobat too. So, you know, in a way, if you had an ET coming from, you know, an Earth and really looking at this system, he would not be able to tell whether the oranges are controlling the acrobat or the acrobat is controlling the oranges. In the same way, the environment is, controlling the system and the system is controlling the environment. So always keep that in mind, that, kind of the context is highly, highly important. So this is another example where actually the shape of these, this is extremely popular now in bionanotech, to actually use the topography of surfaces to control the cell fate. So in this case, they use these, actually different shapes. You see the star shape, the prismatic shape, and they were looking at the differentiation of these cells inside. So basically the cell fate becomes really completely different whether they see them in a star-shaped well or in a pentagon well or in this well, which is pretty cool. Like, how do cells know? Because you have like thousands of cells seated inside of each of these wells. So what is the signaling happening there? Like, how do cells know that they are being seated, like, not in this well, but in this well? Like, you see the difference between these two. It's incredible. Okay, principle number 6, which is kind of derived from this, is that an interface is the key determinant of any outcome. The interface. And I was recently talking with a professor, and I told him I do this bio-nano. He said, "Stay away from me. I don't want to do that. That's this new field, and like, I do surface science and I do interfacial science, and that's actually the key to everything." And I say, you know what? I completely agree. I completely agree, but I'm a young scientist and I need to become, more competitive. So I need to rely on these little tricks, which includes using these fancy words. And I fully agree with that. That the surface and interfacial science is the basis of explaining a lot of these phenomena. So for example, the water in a glass, like here, and 70% of our bodies is water, and that water inside of our bodies and this water are two completely different chemicals. They behave completely differently. Why? Because almost the entire water in our bodies is actually interfacial water in the cell, and it's actually acting as a powerful information carrier. So the properties of these two types of water are like two different chemicals. So you see actually that the properties, including the infrared, or I don't know if this is infrared, this is not infrared. But anyway, the optical signal from the water is different depending on the size of these water droplets inside of the reverse micelles, which are mentioned. So that's basically, let's skip this. So that's one thing to keep in mind. Number 7, surface charge. So if you look at the particles, and if you try to determine their properties, they might have the same composition, the same morphology, but the surface charge will be different. And that's particularly critical when it comes to their interaction with the cell. So look at the red blood cell. If you look at the red blood cell and you measure the zeta potential, you'll realize it's actually 15 millivolts, which is right at the boundary between instability and kind of relative stability. Now, why is that important? It's important because if the zeta potential was higher, if the surface charge was higher, the blood would not be able to coagulate. The open wound would mean kind of bleeding out. And if it was smaller than that, then these things would coagulate already in blood, and that would get thrombosis, right? So you don't want to have that. You don't want to have either. And that's often the case that we see in biological systems, that the stability is always achieved as this critical boundary between instability and this metastable stability. So you never have these stable conditions. Kind of biological systems are always walking on the edge. You remember the Crossroads I mentioned, so that's kind of like that. So Okay, so this is another example of surface charge, again, coming from my research. So we were, when I was a postdoc, I came to the United States. I was in Europe, did my PhD, and then I was invited to do this postdoc. And I was working with this 84-year-old gentleman who was carrying this honorary title. He was the most famous colloid chemist in the world. So he was a very difficult person to work with. So he told me, you either make these uniform cholesterol particles, which no one has ever made at that point, or you go home. And so, and there was this Romanian scientist before me, and he handed me his data, and he was basically fired after a year. And so after a couple of months, I was failing. And he said, you know what, you have just very limited amount of time and you're just going home. And I thought that that's it. I've seen America. You know, I actually never wanted to live in America. I was just curious because I wanted to work with that man. And so, and finally one day I didn't know how to approach the problem. So I decided to use a lot of intuition. You know, I would basically, randomly pick the numbers and I would just look for the light. You know, I know it sounds very weird, but I think you, given that you come from a different culture, you probably understand this better than my Western colleagues. For them, and they're used to logic and logic only, they do not understand this, right? But I believe that this type of approach is more common to you, which is using intuition. And I got that, and I got these particles. And actually, we managed to publish that, and that's how I got my another postdoc, and then I became American citizen and so forth. So anyway, but this I'm showing you because if you change the pH, when you change the pH, you changes surface charge on the particles. So you can make these particles stick together like these sandwiches, right? And if you look at the zeta potential versus pH, you see the zero, which is when there's no surface charge and when there's propensity to aggregate is very high, is here. And the same thing happens when you add salt. Now, so yeah, I've gone too far. So I think I'm gonna, not mention that because it's going down. And we don't have much time. We have 15 minutes left. This is dynamic light scattering. I don't know if you're familiar with this technique. But anyway, you could actually, if you look at the zeta potential here, the dark dots, you can figure out that actually it's very low here in this region. And if you run the reaction between two components in this region, you can create actually structures that are, I'll skip this because this is too much information. Too much information. The point is that, yeah, you can create structures that are actually very similar to in vivo. So, I'll go through that. Don't worry. But so the 7th or 8th future belongs to composite nanoparticles. And I mentioned that here. I mentioned these particles, and I'll just, we'll just, swiftly go through because we already talked about this. These are surface functionalized particles. This is one example where you have a very exciting particle ordering. So, I mentioned colloidal crystals. This would be the simple colloidal crystal where you have a kind of like a symmetrical arrangement of these particles. But this would be a super lattice where you have a, like a more complex ordering, and this would be a quasi-crystalline super lattice, like something really, really crazy. And this is a part of our research as well, where actually these composite nanoparticles perform really well. Silver nanoparticles coated with a polymer, and then you can insert in a lot of things there. Now, complexity of these particles, clearly, actually, I think the first picture was very nice. Or actually, we can, yeah. So anyway, so that is the future, and I think you should be aware of that. So nanoparticles, where each nanoparticle is not just gold nanoparticle or so, but has multiple parts and multiple functionalities. Quite important to keep in mind. But on top of that, keep in mind that simplicity is the key. And simplicity is what I really try to achieve, at least in my lab. This is one of the guiding principles coming from Fritz Schumacher. Fritz Schumacher was yes, he was he was engaged a lot